that NMR can be absolutely superficial. You can simply say that you have a sample under the magnetic field, you give a radio frequency that you observe. The fact is, NMR is not superficial. NMR is very intricate, very refined, very interesting, bit tricky at times, very difficult, but exciting science. And as I said, that everything in NMR spectroscopy is weak. The population difference is less. Signals are weak. Sensitivity is always a problem. And as a result, because of these problems and the fact that it is so absolutely useful, people have invested a lot of money, efforts, and time to make it usable. And the main driving force in NMR spectroscopy was always the sensitivity, and later was interpretation. Because then people realize that when you have 1,000 peaks in your 1 to 10 scale, there is no way you can hit it. So you need to do something different. Anyway, so we have been diving into this very important equation, which came from this. Okay, so as I mentioned that when you place your sample under the magnetic field, permanent, everlasting, ever-present magnet. When you start an NMR machine, you have a magnet. And when you discard it, only then you decommission the magnet. So magnet is always present, is ever-present entity. And started from permanent magnet, which were very small at that time, maximum to the magnitude of about 15 megahertz. At some point in time, I tell you that magnetic power is actually measured as Tesla, but I will keep saying megahertz. You also use word megahertz for different machines, 300 megahertz, 600 megahertz, 700 megahertz. This is nothing but the frequency of hydrogen, proton. Okay, so somehow this new nomenclature, which is a misnomer, and also to some extent is wrong, that we often mentioned magnetic power of magnet as a megahertz, but it is actually the actual measure is Tesla or watts. Tesla is the most common one. So it's a very small machine, permanent magnet, and then people move on from permanent magnet to electromagnet, and from electromagnet to superconducting magnet. And now superconducting magnets are so absolutely advanced, and new novel alloys are actually used, such as niobium, tin, various different kinds of metals are now used to construct magnets. But this is what exactly happened. This is a nucleus of an element which is NMR active, means either it has an odd number of electrons or odd number of protons, and it has a spin, which is this one, axial spin. Okay? When there is no magnetic field. Okay? And it is degenerated. They are oriented everywhere on the face of the earth. But when you place them in the magnetic field, under the magnetic field, when you have sample under the magnetic field, then two things happen. One is that they divide themselves orient themselves into energy states, either two energy states or more quantized energy states. Let's assume the most common, most usable, most frequently used nuclei such as carbon-13, proton, NMR, F19, P31. These are spin-half nuclei. They have dipolar. They have either up or down. There's two energy states. And one thing, once you place the magnet, once you place your sample under the magnetic field, then these energy states are created, and both energy states are populated. Very unlike of UV, IR, X-ray, etc. In UV, IR, Raman, every type of spectroscopy technique, everything either on low energy state or a high energy state if you give them energy. NMR is different. NMR has population in both energy states. So NMR is the only technique in spectroscopy where both energy states are populated. Okay, this is one important feature which we will discuss. Second thing what happened is that these nuclei, nucleus in this case, if you see as example, it start angular momentum called precision frequency or Larmor precision frequency aligned to the magnetic field or opposed to the magnetic field. This is called precision frequency. And this precision frequency is different for different elements, is different for different protons of the same element of carbon, because this directly proportional to V naught, magnetic field. The stronger the magnetic field, higher the precision field. And you make it absolutely crazy, you know. You have a lower magnetic power, it's moving like this. When you have a very high magnetic power, such as 23 Tesla, 1 gigahertz, 1000 megahertz, the precision frequency is absolutely fast. And this precision frequency, which is sometimes called omega, this is the velocity of this angular frequency is measured. This is your NMR signal. Problem is that you cannot measure it directly. You cannot place your detector here. Remember, it's a horizontal magnet. You know, your magnet is like this, horizontal magnet. Magnetic power is directed on the Z and negative Z, right? And your sample is orienting like this or like this. You can never place a detector on top of it. It cannot detect signal because there's so much of magnetic power that it cannot really differentiate between these tiny little. So detector can never be placed on south and north pole of magnetic power. So detector has to be somewhere else. Okay. Now, if you wish to, this is the low energy state, right? Because this is allied to the magnetic field, V naught. This is allied to the magnetic field. If you wish to bring that nuclear spin from here to here, opposed to the magnetic field, you need energy. That energy is radio frequency. Okay? Radio frequency which matches with the frequency of this one. Only that radio frequency will be absorbed, which match exactly with the precision frequency of the element, the nucleus. Okay, this is simple quantum physics. This is your photon, which is like a small sandwich of an energy. This is your precision frequency, right? If you want precision frequency or this nucleus to get this photon energy from radio frequency, it has to move like this on the same speed. Only then the sandwich go from one hand to the other hand. Okay, so the simple quantum physics that only that frequency is absorbed, which match exactly with precision. Right? Fundamental basic concept.
What is the absorption frequency? So change the development what the effect of this.
Okay, so in the classical NMR spectroscopy was a very simple one. You know, you want to measure radio frequency, you want to measure the precision frequency. Simple. You bring radio frequency, you match it, it absorbs, you know. Okay. So there are three different precision frequencies, like in ethanol, you would have three absorptions and you get three signals. But NMR has actually moved, you know. NMR has, back in 1970s, NMR has gone absolutely out of the absorption domain. It becomes something different, which we will delve in and we will try to understand. Okay. So don't please worry much about it. Just try to understand through problems. So I'm going to tell you about the problems. Okay, what is Lamarck frequency? See. Now I'll ask you first. What are the factors on which Lamarck frequency depend? Magnetic field. Remember, I gave a big sermon about magnetic field that every it is B effective. And B effective is different from the V naught because every proton has its own microelectric electronic. Okay, so number one, B naught, magnetic field. Number two, B effective, the electron shading around it. Number three, the nature of magnet. You know, proton is different from carbon. Carbon is different from deuterium. Deuterium is different from phosphorus, fluorine, nitrogen, oxygen. They are different. Exactly as if you have a permanent magnet and you have a steel, you have copper, you have a zinc, you have tin, you have different things. And if you try to attract this magnet, permanent magnet with these needles made of different metals, they would have a different response. So it's called gyromagnetic ratio. Their capacity to respond to magnetic field is called gyromagnetic ratio. That we would also, we will go highly repetitive. So we have gone through this. So this is extremely important equation. Very, very important equation. So you see, this is your omega, lambda precision frequency, directly proportional to the V naught, applied magnetic field. It's called applied magnetic field. And if you remove the proportionality constant, this direct proportion is actually dependent on gyromagnetic ratio or magnetic gyric ratio. Everyone is speaking differently. Some people say magnetic gyric ratio. Some say gyromagnetic ratio. Everybody is just different. I use the word magnetic gyric ratio or gyromagnetic ratio. Anyway, and this frequency, more frequency, more You know, for hydrogen, magnetic gyric ratio is same for all hydrogen, right? For carbon, magnetic gyric ratio is different from hydrogen, but same for all carbon. Magnetic gyric ratio between proton and phosphorus and carbon are different, but for same element, magnetic gyric ratio is different. The only thing which is really making all three protons of ethanol different is actually be effective, right? That is the game of the day. That is what really make this technique so absolutely powerful, because you know exactly what will happen. If you want that system to absorb energy, it has to match with the incoming radio frequency. Lambda frequency must match with the incoming radio frequency that caused transition. Again, you record absorption. It must match. So if there are three different types of protons, there are three different types of precision frequencies. Therefore, three different types of radio frequency. And they're going to be three different signals. Again, so this is the fundamental basic of absorption. So this is the basic of the NMR. Okay. This is the radio frequency which you get. Okay, also in NMR spectroscopy, which yesterday, the day before yesterday, somebody asked me why we keep this magnet up. Geometry is very, very important in NMR spectroscopy. You see your nucleus spin are moving like this. Angular momentum, because this is the direction of B naught. If you want to give a precision frequency, what is the best angle? So radio frequency. In order to have the system absorb energy and go like this, which is the best angle for giving radio frequency? You can't give from above, you can't give from bottom, it's perpendicular. Okay? So geometry is very important. If you don't do that, the radio frequency, tiny radio frequency would be just part of a very large magnetic field and would lost be somewhere. And this is the reason why radio frequency is mentioned like this. You know, so it is perpendicular, always perpendicular. All NMR experiments, when we will discuss about pulse NMR spectroscopy. This is your system. This is the radio frequency. It must match. Then it goes down. It's called excitation. Okay, you record absorption. If you're not interested in absorption, you record replication. Both of them should be same, right? Either you record absorption, or it eventually will lose and relax back and achieve thermal equilibrium. Every system which you disturb, even human system, will go back to this thermal equilibrium, right? So the energy which you have given to the system, it will go out of this system, and this process is called relaxation. You have a choice. You can record absorption, or you can record relaxation. That you don't need to worry about it, but you have an option. Okay. So radio frequency must match with normal frequency. Okay. Only then you would have precision nuclei moving from Z direction to minus Z direction. Okay. And it's called flipping. It's called spin flipping. nomenclature is also important. So flipping. Flip from this to this. Flipping. And NMR spectra. And why you are giving radio frequency, by the way? If you could any means had the ability to measure precision frequency without any intervention, there was absolutely no need of radio frequency. Right? If you can measure precision frequency without, but you can't measure it, you know. You have to have a matching radio frequency in order to measure the precision frequency. Okay, that is the reason you need radio frequency. Because without radio frequency, you cannot measure precision frequency. Okay, so this is what happened. Now, let me ask you a question. Do all nuclei, the same element, will resonate at the same element? Will resonate with the same downward frequency? Why not? If you are physicists, you should be super confident that they would all resonate at one frequency. Because they have built such a beautiful machine, they invested a lot of time, effort. They want to see hydrogen, all hydrogen as in one peak. Why not? So they have different microelectronic environment. And this makes NMR spectroscopy super useful technique because it helps you to measure this microelectronic environment, right? And this makes you to understand how many different types of protons you have when you're measuring hydrogen, or how many different types of carbon you have when you're measuring carbon-13, or how many different types of nitrogen you have when you're measuring N15 or whatever. So be effective is based on microelectronic environment around a specific nucleus. Electronic shielding due to inductive effects, magnetic anisotropy, hybridization, and so many factors. The most important is that electrons are shielding. Electrons have a counter-magnetic field, which oppose the magnetic field B0. Therefore, the nucleus will feel a magnetic field which is different from B0. Okay, so this is the basic concept. The protons which are exposed, which are de-shielded, which are next to an electronegative atom such as chlorine or oxygen or nitrogen or fluorine or whatever, they will be de-shielded, and their B effective would be close to B0, and the Raman frequency would be very high. So, but I wish to tell you the difference between hydrogens and this microelectronic environment is not that much. It's not in megahertz. It's only in hertz. Remember the difference between ethanol and this tiny little spectrum between 0 to 10 is just very minuscule. The energy difference is so minuscule between them, and that is the reason you need to have a super fast detector. And this was also, I told you that theoretical and conceptual and technological difficulties which make NMR one of the last techniques developed. And NMR in spectroscopy was largely because detecting these small signals also. And also, I wish to remind you the difference between low energy state called alpha, which is aligned to the magnetic field, and opposed to the magnetic field. We'll have energy diagram. How much you think it is?
It depends on the magnetic field of one.
I mean, of course it depends, but in general, when you shine UV and you take from lowest unoccupied molecular orbital to bromo, all these electronic transition goes from up to bottom, from bottom to up. You know how much energy you need to have? Somewhere between 30 kilocalories to 160 kilocalories, depending on the nature of it. So much energy you need to have. For IR, for the bonds to stretch, you need to have at least about 1 to 2 kilocalories. In NMR, the energy difference is only a part of a calorie, 0.004 calorie, not kilocalorie. Imagine this is what you're measuring. And what kind of detector you need to have for that? It's a nightmare. And that is the reason when the difference between the energies of two energy states is so little, this is not surprising that both energy states are populated. If the difference is big, the species can't go from one to the other. If the difference is so little, then both energy states populated because the difference is not so much. They go up and down, right? And the slight axis in lower magnetic field, lower energy state is what absorb your radio frequency. It's called Boltzmann distribution axis. The name of the person who first discovered. Don't worry about that. No tashwish, no problem, no issues. Okay. This is what I was saying. In the absence of magnetic field, no energy state, no radio frequency absorption, no precision frequencies, right? Nothing. Life is so easy, right? When you place that under the magnetic field, then in the dipolar nuclei, you have two energy states, low energy state and high energy state. And the difference between low energy state and high energy state is directly proportional to V naught. Also, lower frequency was also dependent. The difference between the energy state is going to be directly proportional to V naught. The stronger the magnet, the larger the energy difference. You bring more, and then you get more energy difference. I ask you a logical question. You expect to have more difference in population between two energy states when you have a larger energy difference or less?
No,
When it becomes difficult for the nuclear species to jump over and down, then the difference between them is going to be higher. And when the difference is going to be higher, your signal would be stronger. And this is the reason why people are investing their lives and money for developing high resolution, superconducting, big NMR machine. You have a strong magnet, more energy difference, more population difference. Okay? Yes, sir.
Sir, and जब हम इसमें magnetic field apply करते हैं, तो लाजमी नहीं कि दो ही स्टेट बनेंगे, तीन भी बन सकती हैं, चार भी बन सकती हैं। हम उसमें कैसे डिफरेंस करेंगे? This is lower energy state and high energy state and +1/2 and -1/2.
Okay, so for every element, there is a spin quantum number I. There are elements which have only two energy states. There are elements which have more than two energy states. And in that case, we can have 4, 5, 3, 6, 4, 7, 8 energy states. It becomes increasingly difficult to detect them. Very simple reason. When we have a problem with two energy states that both populations are populated, if we have 7 energy states, all populations are, and the difference between them is going to be even minuscule. And that is the reason that quadruple nuclei are often not detected. Although they are NMR active, but minuscule energy difference which exists between two energy states, if we have 6 energy states, the difference between quantized energy state is going to be even smaller. And that is going to be very, very difficult to detect. Okay? So, I hope you appreciate this, right? You understand. And this is the reason why you have stronger and stronger magnet. I said that major driving force in the development of NMR spectroscopy was initially, until 1980s, for more sensitivity. If you can detect less amount of sample by having a large magnet, then it means that your technique is more sensitive. So people who are investing in the price is exponential. See, if you wish to buy, you have an NMR in Venezuela, right? It's about 400 megahertz. Okay, this 400 megahertz NMR machine is about, I would say, 400,000 USD, 0.4 million USD. Okay. If you go for 600 NMR, 600 megahertz, you don't really expect to have it in 600,000. It's going to be 1 million years, exponential. And if you want to have a 1 gigahertz machine, 1000 megahertz machine, this will cost you a fortune. It will cost you something like 6 million, 8 million, 10 million USD. These are very simple. Magnets, I have seen how they make magnets. If you go to France, you see they actually make magnet by hand. There is no machine developed which make magnet by automatic. Magnets are made by hand. There is a cylinder, they put medium coil around it, exactly as mothers make sweaters for granddaughters or grandsons. Okay, so they do it exactly. Larger the magnet, all their life is spent on coiling it by hand. The chances of breaking it is so high because these are not steel wires, these are niobium wires. Niobium is a very fragile element, and when they break it, the cost goes to you. You should pay for it. This was their fault, but customer should pay. And this is the reason that large magnets are exponentially expensive. Exponentially expensive.
Doctor, what about the place we put this NMR device? Cannot affect about the environment? You can affect by this magnetic hardware.
Yeah, that is a major problem. Even this super shielded NMR machines, they call ultra shielded. We have it. Some of our NMR machines, but I think 5 of them are normal shielded. Some of them are ultra shielded, some are super shielded. Even in these NMR rooms, you cannot really go with a magnet. God forbid if somebody has a pacemaker and a fit, alas. So you don't go with that. And you don't go with watch, you don't go with the mobile telephone, you avoid it. Exactly as when you go for MRI, this is a much smaller magnet. It's 1/10 of what we have here. And even there, they actually ask you to remove everything. So these magnets, despite the fact that they are ultra shielded, they have very specific alloy and metal containers through which they protect the magnetic. Still, there is a hazard. Okay. So,
I would like to share my little bit experience. And you sent me to Rupert, Switzerland for the training. So I visited the magnet facility and I met the engineer and the girl who was actually working to wrap this coil. And I see myself, and there is now a motor that is very, very slow, like few meters every day. He was able to hold it around the coil. And I discussed with her, so she said, as the magnet is larger, for 300 megahertz, for example, about 80% are okay. But as
20% break.
yeah, yeah. And
Because more coil and
yeah, and as it goes higher and higher for like about 800, he said 20 to 30% are okay, and then the rest are yeah. So it's very, very slow. He has an instrument.
it means that cost of production is very, very high because failures are high also. And that is the reason why these NMR machines are really very expensive. Okay, so move forward. Okay, now question: explain the behavior of spinning nuclei. The spinning nuclei in the absence of magnetic field. Shabash. In the influence of magnetic field. Line and line has precision. And when radio frequency of the appropriate wavelength, matching wavelength is provided there. Beautiful, very impressive. Okay, and so you see, not only hydrogen, proton, carbon 13, chlorine 19, T31, and 15 are measured, but there are other nuclei measured also. Organic chemists are much more interested in two elements, hydrogen and carbon. The biochemists like Dr. Atia, they are interested in nitrogen as well. Okay, people who are working on nucleic acid, they are interested in phosphorus as well. Right? People are working on different kind of cyclic ethers and crown ethers, they are interested in oxygen as well. So depending on the interest in the type of chemistry, people use various kinds of elements and they have different behaviors. So for instance, nitrogen 14 is NMR active, right? Why it is NMR active? Okay. And it is major isotope. 99%, 99.6%, so thank you, is L40, right? Even then you can't detect it. That's a problem. People have to enrich their sample with L15. They have to build, construct, synthesize their proteins and molecules with N15 label. Why nitrogen is not detected, despite the fact that it is NMR active, is this one. Quadrupole. Only 3 energy states. Number one, that these three energy states is so absolutely close to each other that even in the strongest magnet, it's so difficult to measure the energy difference. Flip-flop between three different energy states is so difficult that it's so difficult to measure the signal. And this is the reason that in natural abundance, nitrogen 14 is not detected. On the other hand, if you want to detect N15 in natural abundance, N15 is only carbon is about 1.1%. N14 N15 is about 0.36%. Such a minuscule natural abundance that if you take a sample, the possibility of N15 is only 0.36%. So it's so damning, that it's very, very difficult to detect. On top of it, its gyromagnetic ratio is very poor. It's 1/6 of Hz. And then on top of it is a quadruple nuclei. So N14 is not detected. Is often not detected unless there are other things like symmetry and other. So these are problems. N15, on the other hand, is a natural abundance. It's difficult to detect. But you see, protein chemists all the time are synthesizing N15 labeled proteins. They know the structure. They know the sequence. They're only trying to get the structure three-dimensional configuration. So they can construct their protein in the presence of labeled N15. In fact, they are double or triple labeled. Sometimes if they have money, they go for deuterium, they go for carbon 13, and they go for N15. Deuterium to nickel. Triple labeling करते
nitrogen, carbon, and
deuterium. That is what I said. Thank you. So, they construct for E. coli to synthesize protein, they don't give a normal medium. They give carbon 13 labeled glucose. They give N15 labeled ammonium hydroxide, ammonium chloride, and they give a heavy water, E2. And when they have protein, all nitrogen are N15. They're happy people, although they spend half of money of the institute. So, and N15 is a spin half nuclear. Is a spin half nucleus, and we do allow energy states. Natural abundance, of course, difficult, but in biomolecular protein, where people label their proteins, is a beautiful nucleus because all nitrogen. I'm not very happy with that. So, because all nitrogens are N15, and as a result of it, they get labeled, and N15 is 100% abundant because there's nothing else. They constructed their protein with N15. When you grow, of course, you know that these are gene products. So when you grow E. coli are labeled. Recombinant synthesis of proteins. So E. coli are designed to produce these proteins. These tablets are incorporated, and E. coli synthesize them in the presence of a media which is labeled. Okay, so glucose required, ammonium chloride required, heavy water required, they all are labeled. Therefore, the the protein which is synthesized is triply labeled. If they don't have money, they go only for N15 and carbon-13. Even if they are poor, then they only go for N15. The carbon-13 is reasonably good, is about 1.1%, and you can use it. So triple label, double label, single label proteins are expressed. So similarly, oxygen is silent. Why oxygen is silent? Main isotope of oxygen is silent.
Even number.
So what is even number? Why all even number are silent? Even number of protons and even number of why are you upset that I think? Okay, thank you. Yeah, because even spin, the nuclear spin, the spin of the nucleus is dependent upon the spin of nucleons. Nucleons are the particles which are within the nucleus. So if they are paired, there is no net magnetism. If they are unpaired, then there is an axial spin, and this is called spin angular momentum. The speed with which they are moving around their own axis is called spin angular momentum. But when they move around in the presence of a magnetic field, it's called magnetic moment. These are terminologies which you need to learn with time. So oxygen 16 is not a very good. It's of course NMR silent, and oxygen 17 is 5/2 spin quantum number. 5/2, 3/2, 1/2 plus, and then minus 5/2 minus 3/2 minus 1/2. 6 energy state. God, it is just so scary that you cannot really measure anything out of it. Very low natural abundance, even lower than the nitrogen. Even lower than the nitrogen. Very, very low natural abundance. People are still trying to, there are some intelligent people who are trying to detect N15 and N17 in their natural abundance. So there are still people working on it is because and it's only possible when you use sensitivity enhancement by different, and we will go for sensitivity enhancement with deuterium. Deuterium is NMR active. Deuterium is NMR active because one proton and neutron. So with 3 allowed spin state. So it's a quadruple nuclei. And deuterium is often difficult to measure. So you see that natural abundance of deuterium is only 0.16%. Is even lower than oxygen. Oxygen 17. So deuterium in natural abundance is not detected. And if you wish to detect deuterium, then you need to label it. So deuterium is detected, but only when you label it and you make it more abundant. Okay. Chlorine 35, 37 are NMR active. They are okay, because they are nearly 50% natural abundant. Hina is watching me because there is an AI course which is at 1:30 of the same Zoom link, so I'll finish it. F19 is a wonderful nucleus. Is my favorite because the galvanic ratio of F19 is so similar that with a fine tuning, you can measure it with along with hydrogen, in place of hydrogen, because its F19 is about 99% naturally abundant, spin half nuclei, And also, gyromagnetic ratio of fluorine is close to hydrogen. So if you have a fluorine, you should be a happy person because you can detect it without any difficulty. P31 is a spin-off nuclei, 100% metal abundance, extensively studied by people who are working on phospholipids and nucleic acids. Okay, so at this stage, I go offline and I'll discuss with you. Thank you very much, online participant. Yes.
Why detector cannot be placed at North Pole?
Okay, this is fine because detector is supposed to detect this tiny little radio frequency absorption. You know, no detector can survive. No detector can survive at the magnetic power of Tesla. It will burn like this. Exactly. Okay. So therefore, detector can not only be placed on North Pole in the direction of magnetic field. Absolutely impossible because even if you use the strongest detector, it would be detecting only the magnetic field, not your tiny little signal of precision frequency. So detector and radio frequency both have to be perpendicular. The radio frequency has to be perpendicular and detector has to be perpendicular also. Thank you. Good question.
Detection depend on gyromagnetic ratio, more ratio is detection.
Yeah, there is some relationship between gyromagnetic ratio. If the gyromagnetic ratio is high, then the spinning of nucleus is much higher than the low gyromagnetic ratio, and therefore you would be able to get a stronger signal because precision frequency is much higher. Precision frequency of hydrogen is about 60 times higher than the carbon. So the radio frequency which you need is going to be 60 times higher than carbon. Therefore, you would have a good detecting strong signal. We go offline. Sorry, we go offline. Yeah.